is evaluating limits analytically. Okay, we're going to be encountering things that look like this. Limits as x approaches c of some function f of x. And basically, there are going to be several different cases. And we're going to go over two today. So the first case is that f of c exists. In the second case, f of c does not exist, but the limit does exist. And in this particular case that we'll examine today, f of c does not exist, and specifically, it equals something like 0 over 0. All right. Is 0 over 0 defined? No, right? Because we're dividing by 0. But the limit is still going to exist. Okay. I'll give you guys an example. Let's say we have something like this. Let's say we had f of x equals, let me think of something, x squared minus 2x minus 3 over x minus 3. Okay, so we have a quadratic over a, how do you call this thing? Binomial? Anyways, the point is, this is a function that we care about when it comes to limits, because let's say we tried to evaluate f over 3. What would be the numerator? What would the numerator be equal to? 0, very good. That's because 3 squared minus 6 minus 3 is 0. So the numerator is 3 squared minus 2 times 3 minus 3, which is equal to 0. Now how about the bottom? What is that equal to? Also 0, very good. So this is going to be equal to 0 over 0. So, technically, this function does not exist at the value x equals 3. Yet, the limit is going to have a well-defined value at x approaching 3. Limit x approaching f of x, limit of f of x as x is approaching 3 is actually going to be well-defined. And we can see this graphically, because if you were to graph this function, can anybody guess what it would be? What would the shape be? Wrong. Any other guesses? Very good, a line. Who said that? Very good. It would be a line. Let me see, where would this line be? It would be here. It would be a line, but there's actually going to be a hole. We saw several of these in our homework, right? There's going to be a hole at x equals 3. Why x equals 3? Because the function is not defined there. But actually, this is going to be the line x plus 1, just with a hole. This line is f of x. Okay? So if I were to ask you guys the question, based on this graph, what is the limit as x approaches 3? What would the answer be? 4. Very good. 4. Okay? So it's quite obvious from the graph, but let's say we're not allowed to graph this. How would we find this limit? Right? Let me go to a new page. Okay, what is my function again? We're trying to find limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3. Well, if I wanted to find the limit without graphing, the first step would actually be to factor the numerator, okay? So I'm going to write, I need to keep this limit sign here, okay? Very important. Anybody want to factor the numerator? it's not a factorization.
X minus 2, or parentheses.
Close.
Parentheses x minus 2, parentheses.
Anybody?
X minus 3, x plus 1.
Very good.
Oh.
Oops.
What are you talking?
It would be x minus 3 over x plus 1. Okay? It's just hard to do it in your head, but I'm sure you guys could all do it. Over x minus 3. Okay, and what do we notice about this? Yeah, very good. The x minus 3 cancels out. So we're actually left with limit x approaching 3 of x plus 1. And if we plugged 3 into this function, x plus 1, we have no trouble at all, right? That's just 4. 3 plus 1 is 4. And so this limit is actually going to equal 4. So that's how we figured that out, okay? So today we're going to be encountering several examples of those situations where the numerator equals 0 and the denominator also equals 0. But if we do some factorization and then canceling out, we're actually going to be able to evaluate the limit pretty easily, even though the function is not defined at that specific x value. Okay? Okay, let's actually return to a more simple example though, okay? So sometimes you're going to encounter questions. Actually, no, let me do it this way. Let's talk about the process for finding a limit, okay? Process for finding a limit. Okay, just assume you guys can read that. Okay, the first step, you guys have seen flowcharts, right? So the first step, we're going to ask ourselves, let's say we have a limit, question. The first step is we're going to ask ourselves, can we evaluate, or no, let's say, is f of x defined at x equals c? Okay? Let's say we have a question about the limit as x approaches c of f of x. Question mark? Okay? So the first question we want to ask when we evaluate a limit is whether f of x is defined when x equals c, right? The question is asking what is the limit of f of x as x approaches c. But if it's defined at x equals c, then the answer is just f of c. So if the answer is yes, then our limit is actually going to simply just be f of c. Limit of f of x as x approaches c is simply going to be equal to f of c. Okay? So just as a quick example, let's say we had a question that's like, what's the limit as x approaches 1 of 1 over x? How would we follow this simple flowchart in this example? In this case, is f of x defined at our c value 1? Yes? Who said, is the function 1 over x defined at our c value, x equals 1?
Yeah.
Yes, it is, right? Because 1 over 1 is just 1, right? So in this case, all we need to do is simply plug in the value we have for c, which is 1, and we just need to plug that into our function, and that's the limit. So the answer is 1. Very easy. Okay? So a lot of the questions you'll have in the homework are simply like this. It's asking you for a limit, but because the function is well defined at that specific value, the limit is really easy to calculate because all you need to do is plug in that value. Okay? So in this case, f of x is defined at x equals c, so all we do is plug in the value, and the answer is yes. But sometimes the answer is no, right? Sometimes the function is not defined. So the answer is no. Like in our previous example, right? In our previous example, is f of x defined here when x equals 3? No, right? Because the numerator is 0 and the denominator is 0. So in this case, we need to kind of split into some more different cases, okay? So if the answer is no, we are going to go over 3 different methods of evaluating limits today. The first is the one that we've already seen, which is factoring. Factoring and then canceling. The second one is going to be rationalizing the numerator. Right, you guys all know how to rationalize the denominator, but today we're going to be rationalizing the numerator. And the third possibility is use a trig limit identity, and I'll explain what I mean by this later. Okay, 3 possibilities. And we've already seen the first one, so that's great. Okay, and these 3 cases are helpful when the function evaluates to 0 over 0. 0 over 0. So like in the previous example, our function here was 0 over 0 when x equals 3. So we needed to apply one of these methods. And it turns out the first one was the most helpful. Okay? So I'll give you guys maybe another example of the factoring and canceling, so you guys can practice that. Are we all good with this slide? Yes, we are.
Can I take a photo?
Sure. 3, 2, 1. Okay, you guys can try this on your own. Let's say we had the limit as x approaches -3 of x squared plus x minus 6 over x squared minus 9. Okay, try this on your own, please, or with your partner. Thank you. And try to apply this flowchart, okay? Apply the flowchart. So the first question you need to ask is the function defined when x equals -3? Is the function defined when x equals -3? So you need to plug in -3 and see what happens. Okay?
What do you ask? You're asking if it was word, like, it'd be undefined.
So the first thing I'm asking you guys is to plug in x equals -3, because we have x approaching -3. So plug that into the function first and see whether it's defined or not. Okay, it's not. Rahul says it's not, and I agree with that. It's not because you actually get 0 over 0 when you plug in x equals -3. So we have to use our first method, which is factoring and then canceling. Okay? You guys can please all do that. Questions?
When you factor numerator over denominator,
Hmm?
like with the parentheses, like when you're factoring, when you have like, if I have x plus 3, and then on the bottom is x minus 3, x plus 3, you get rid of the minus 1, right?
Why? You would get rid of what cancels out. So whatever factor is shared.
So the same, it says the ones that are the same. It's like the ones that are opposite or the same?
You can only cancel the factors if they're the same.
Okay.
Yeah.
Yeah. X minus 2, and then x minus
Okay, I'll show you guys the first step, which is to check x equals 3, which you guys already did, presumably. Check. Plug in x equals -3. Okay, so indeed, when we plug in x equals -3, it's not defined. It's 0 over 0. So we need to do the factoring and canceling thing. Okay, do we have an answer? Anybody? 5 over 6.
5 over 6.
I haven't actually done it, so 5 over...
Yeah, 5 or 6.
It's too hard to do in my head. Okay, let's just do it together. Super important. When you guys do limit problems, you need to keep writing this limit until the limit is evaluated. Okay, so you guys need to write this for every single step. Miss Lee told me that she takes off points if you don't do that, so I will be following suit.
If what?
Hmm?
Take off points if what?
If you do not keep writing this for every single step that you do. Okay? So if you just went straight away and factored this thing without writing this limit before the function, then you guys would lose a slight amount of credit, but not a lot. Okay, who has the factorization? One high true. Just shout it out.
Wait, x minus 2 or x minus 3? X minus 2, x plus 2.
Top and bottom. I need top and bottom.
X minus 3 over x plus 3.
Over
X minus 3. No, wait.
X plus 3.
X minus 2 over
Hey, okay, can somebody raise their hand? Okay, Brock, okay, sorry.
So the top is x plus 3, x minus 2.
Mm-hmm.
X minus 3, x plus 3.
Okay, very good, thank you. The top is x plus 3 times x minus 2, and then the bottom is x plus 3 times x minus 3. Okay, hopefully we all got that. If you didn't, I forgive you. Okay, and then what happens? Well, we can cancel out the x plus 3's, and so we're going to be left with the limit as x approaches -3. Notice how I'm writing the limit again, because I don't want to lose points. The limit as x approaches -3 of x minus 2 over x minus 3. Okay? Now, is this function defined when x equals -3? Yes, very good, because we don't have any issues with dividing by 0. So in this case, to evaluate this limit, all I need to do is plug in x equals 3, and then I'll have my limit. Okay? So this limit is simply going to be equal to -3 minus 2 over -3 minus 3, which is 5 over 6. I don't know if anybody said that. Anybody say that?
I did.
Audrey, you said that?
And Audrey, but I said before.
I heard 5 over 7 or something, or 5 over
I
9.
said 5 or 9 and then I corrected.
Okay. We'll see. You can redeem yourself with the next one.
No, I changed.
Yeah, no I choose.
Give the Audrey together. Right?
Oh, really?
Yeah.
I don't remember what she said.
She said 5 or 6.
Okay. Okay, so I hope that's clear. Factoring and canceling. Let's go over the next strategy, which is, what is it called? Rationalizing the numerator. So this is best seen with another example. So here we're going to be doing the same thing that we normally do for rationalizing a denominator, except now we're going to be rationalizing a numerator. So do you guys remember how to rationalize the denominator and stuff? Hopefully. So here's a quick example. What do I have here? Let's say we had the limit of x approaching 0. So okay, so this strategy we apply whenever we encounter square roots, okay? So let's say we had this. This limit of x plus 2 square root minus the square root of 2 over x, okay? So that's our question. So question now, when we plug in x equals 0, is this function defined? No. And the reason is because the numerator is going to be 0, right? If x is 0, the numerator is 0. And if x is 0, the denominator is also 0. So here, the first strategy doesn't work, or the first option in the flowchart doesn't work, right? So we need to go to one of these second options here. And because we have square roots, well, the option is going to be the one that's called rationalizing the numerator. And basically, the way that this works is, if you guys remember how to rationalize the denominator, it's very similar, except now it's just for the numerator. We're going to take our original function, and then we're going to multiply it by 1, but in a clever way, right? We're going to multiply it and specially choose, so the square root of x plus 2 plus the square root of 2. Okay? So just like with rationalizing denominators, all we're going to do is take the numerator, and we're going to change the minus sign into a plus sign. Or if it were a plus sign, we would change it into a minus sign. And what this does is that this utilizes the difference of squares formula, and it helps us make the, sorry, this is wrong. And it helps us make the numerator rationalized. Okay? So we're going to basically just multiply by this. And what happens when we do that? Why does this look weird? Give me 1 second. Oh, okay. Never mind. I'm correct. Okay. All we're going to do is expand this and then see what we get, okay? So the top is a difference of squares. Right? You guys remember the formula? A minus b times a plus b equals a squared minus b squared, right? So the top is simply that. So what we're going to have is the square root of x plus 2 squared minus the square root of 2 squared. And then the bottom is going to be x times x plus 2 plus the square root of 2. Okay? Are we in agreement? Yes. And then the top is going to simplify as x plus 2 minus 2 over, and the bottom stays the same. Doesn't simplify. Okay? Well, we can keep simplifying this. The numerator is going to be x, and the bottom is also going to have x, right? So what are we able to do on our next step? Cancel out the x, right? Because in this current form, if we were to plug in x equals 0, it would still be undefined, right? It would still have a 0 in the numerator and denominator. So what we need to do is cancel out the x's. And we're going to have 1 over the square root of x plus 2 plus the square root of 2. And now, this is really good for us, because if we were to plug in x equals 0 into this function, it would actually be defined. We have no issues. So all we're going to do here is plug in x equals 0, and we're going to get 1 over the square root of 2 plus the square root of 2, which is equal to 1 over 2 square root of 2, and then we should rationalize this. So multiply top and bottom by square root of 2, and we have square root of 2 over 4. That's our answer. Okay, easy, right? Any questions? Anson?
Why'd you make x plus 2 minus 2 into x? How'd you get rid of the 2 minus 2?
Because the 2 minus 2 equals 0, right?
Oh.
X plus 2 minus 2. Good question. Anything else? Too easy, right? You guys can do them by yourself? All right, let's do it. It's too brilliant in this class. Okay. Okay. Your task now is to do this one, which is the limit as x approaches 4 of the square root of x plus 5 minus 3 over x minus 4. All right, go ahead. First one to get it can get a high chew. I know the answer this time. This is easier to do in my head. Raspberry. I don't like raspberry, but some of you might. Mm-hmm. No. Nice try. Anybody close? I'll give you guys the first step. The high chew is still up for grabs, whoever gets it. So the first step is going to be multiplying in order to rationalize the numerator. So what we're going to be doing is multiplying both top and bottom by the numerator except with the minus sign switched with the plus. So square root of x plus 5 plus 3 over square root of x plus 5 plus 3. And then the rest of the question is really just simplifying this and getting an answer, which is... Nobody? I'll do one more step. Just shout it out when you get it. The top is going to be a difference of squares. So that's x minus 5 minus 9. Because it's the difference of this square, which is x plus 5. No, close. X plus 5 minus 9, because 9 is 3 squared, right? And then the bottom, well, it doesn't really simplify, so we'll just write x minus 4 times x plus 5 plus 3. Nobody's gotten it yet?
Wait, isn't it a square root over the x plus 5?
Square root over the x plus 5?
Or it's like...
No. You mean this one?
Yeah.
No, it's not, because we have a difference of squares here.
Why didn't you do that in the last problem?
I did. I just skipped a step on the second one.
Oh.
So in this last problem, I actually wrote out the difference of squares, but that came out to x plus 2 minus 2, right?
Yeah, that's true.
Same idea here.
The bottom. Did you skip a step in the bottom too?
Nope. I just multiplied x minus 4 times x square root of x plus 5 plus 3.
I got x.
X is what?
Square root of x plus 5 minus 1.
Minus 1.
Yeah, because 4 minus...
Very good, yes. Ethan, right? You got it? Thank you. Okay, somebody got it. Now you can actually go through it. Okay, well, the top. Okay, any more questions about this step I made here? This is probably the most important step. Questions?
Which step?
The step here. We multiplied by the numerator, except with the sign flipped, and we multiplied both top and bottom by that. And then the numerator is just a difference of squares. That's how it becomes rationalized. That's why it's called rationalizing the numerator, right? So this is just x minus 4 over x minus 4 times x plus 5 square root plus 3. And then this cancels, right? The x minus 4s cancel, right? So this becomes 1 over the square root of x plus 5 plus 3. And then now, since when we plug in 4, we don't get zeros anymore, we can just plug in 4. So this is 1 over the square root of 4 plus 5 plus 3, which is this 1 over the square root of 9 plus 3, which is 1 over 6. Okay? Hopefully that makes sense.
How'd you do the denominator on the third line?
On the which one?
The x minus 4, the one in parentheses, the square root of x plus 5 plus 3, below that one. How'd you get the denominator?
Here?
Yeah, that one, how'd you get the denominator there to the one below?
Oh, okay. All I did was I canceled out these two terms. Right? Okay, this is really the most important step here. The difference of squares and how that expands and how you choose what to multiply by. You choose the correct factor in order to make the numerator rationalized. And in order to do that, you need to multiply by the numerator except with the sign flipped. And this technique you want to use whenever you encounter square roots in the numerator, okay? Got it? Okay, let's move on. You guys can practice this later. And you'll see this on our group quiz too, so it's good practice too. Okay, then the third way is trig limit identities, okay? And these are things that you just need to memorize. The first limit is the limit as x approaches 0 of sine x over x is equal to 1, okay? And I'm going to box that because you need to just memorize it. You could derive it using a theorem called squeeze theorem. It's a very interesting theorem, but we won't do that today. And the second limit you need to memorize is the limit of x approaching 0 of 1 minus cosine x over x is equal to 0. Okay, just memorize them. They are two special trigonometric limits. You just need to memorize them. And you're going to encounter these in questions like maybe these. Let's say we had the limit of, as x approaches 0, of maybe like 5 sine x over x. Can anybody guess what's the answer? No. 5. Very good. The reason is we can actually just take the 5 out of the limit. This is something that's allowed. You're allowed to just take out factors out of a limit as long as they're not equal to 0. And you're able to just do this. And then this is something that we've memorized as equal to 1. So this is just 5 times 1 equals 5. Okay. Any questions about this? Let's say we had something a little more complicated. let's say we were asked, what is the limit as x approaches 0 of tangent x over x? Any ideas about how we could get this limit to look more like what we've just memorized? Tristan? Okay, very good. I agree. If we write this tangent as sine over cosine, then we're able to make it look like what we already know. And that's kind of an important strategy that we're going to use. So tangent x is sine over cosine, so this is sine x over x times cosine x. And actually, we're able to take this cosine x out of the limit because it's not equal to 0. And we're able to write it as 1 over cosine x times the limit as x approaches 0 of sine x over x, which is just 1, right? As we've just memorized. Sorry, we have to actually plug in the 0 for this. Cosine of 0. So this is going to be 1 over cosine of 0 times 1, which is equal to 1, because cosine of 0 is 1. Okay? Let's do, any questions though? Let's do maybe harder one, which is question 16 on the extra practice problems. We're also allowed to multiply different limits together, okay? And this is an example of that. So limits are something you're allowed to add and multiply and subtract from each other. So let's say we have the limit of sine x times 1 minus cosine x over x squared. Okay? Is there anything we notice about this function compared to those two identities that we've just memorized? The numerators are both in the numerator. How about the denominator? Squared. Okay. Yeah, very good. So that's kind of what you were saying, right, Daniel? The identities are essentially just being multiplied. So what we have here is really just the limit of sine x over x times the limit of 1 minus cosine x over x. Right, which is what we just learned, except they're multiplied now. What we're actually allowed to do is consider these as two different limits that have been multiplied together. Okay, and this, well, the left one is just 1, and the right one is 0, so it's 1 times 0, which is 0. Okay? Let me see what I've written for the group quiz. If it's a hard one, I'll go through a different example. If it's easy, I'll just leave it here. But any questions about this? Yeah, Tristan?
You go back up to when you get 1 over cosine. So how did you get x times cosine x equal cosine 0?
Basically, all I did was I took this out of the limit and I pulled it out in front. Okay, and in order to pull it out of the limit, I have to actually plug in x equals 0. Okay? Yeah, any other questions? Yeah, Anson. It would not be 1 times 1 because this is actually 0. I haven't plugged it in. This limit is equal to 0. Mm-hmm. Yeah. Okay, well, the one I've written on the group quiz is not extraordinarily difficult, so I hope this makes sense. Any final questions? You guys can do your homework if not. The homework is, honestly speaking, not very instructive. I did not write it. I don't know who wrote it. Maybe Mr. Nyberg. Yeah, the problem with the homework, in my opinion, is that it just has a bunch of examples where the answer is yes to the first question that we asked. So all you really need to do for a lot of the problems on the homework is just plug in the value of c into your function, and that's just the limit. So unfortunately, there are not many of these examples, which is why I've attached an additional practice problems document that will help you a little more with those. Okay, so next class, we're going to have time in class to review all of these things, and we'll do a lot of practice problems, and then the end of next class will be the group quiz. Yes. Back where? Okay, so next class we're going to be doing essentially the entire review packet together, or you guys will be doing it together, and then you'll have the group quiz last 15 minutes of class maybe. So hopefully you're seated next to somebody competent. Or maybe you yourself will be that competent person, who knows? Yep, you can go ahead, start on the homework. 15 minutes.